And can you see my laser pointer?
Yes, we can.
Okay, good. So should I start now?
Yes, yes, sorry, please go ahead.
Oh, okay, okay. Yeah, so, hello, everybody. Greeting from Tokyo, at the moment. And first of all, thank you very much for Piers and Rajiv, for giving me this, opportunity. And taking this opportunity, I'm going to talk about, Kitaev related topics. And today, I want to speak, mainly about, two, quantum spin liquid. First one is, closely related to, previous talk, by Yuji, Matsuda. And I'm going to speak about, the same, thermal transport in ruthenium chloride. And I want to examine, whether there is, any half quantized, thermal Hall effect, is there any quantum oscillation? And then, second part, I would like to extend, our thermal transport study to, Kagome Harvard Smithite. And I would like to, discuss, spin excitation, whether gapped or gapless. And those, two works were done in collaboration with, my Stuttgart, colleague, in particular, Jan Bruin and Ralph Klaus and Yosuke Matsumoto. And, ruthenium chloride, crystals from Tokyo Institute of Technology, the same, sample source, as Matsuda-san. And, from, Department Lodge in Max Planck. And the Harvard site, crystal, from, Masahiko Isobe in Stuttgart. And I don't have to repeat kind of introduction. Yuji Matsuda gave, beautiful introduction. But anyway, this, game for quantum spin liquid were kicked off by Phil Anderson. He proposed two-dimensional quantum spin liquid RV type 50 years ago, half, century ago already. And recently, we have, new generation of 2D quantum spin liquid, so-called Kitaev quantum spin liquid. And the Kitaev proposed simple but elegant, model. He placed, spin work moment on top of honeycomb, lattice. And the spins are, connected by bond-dependent Ising bond, which, easy axis, X, Y, G, and the conflict of those, three bonds, gives rise to quantum spin liquid state. And as, Yuji discussed, what is, amazing for this, Kitaev quantum spin liquid is the ground state is exactly solvable. And Kitaev, fractionalized, spin 1/2 into two kind of, Majorana fermions called B, localized, Majorana, which represents G2, flux, and the uniform in the ground state. And once, G2 flux uniform, this, C Majorana fermion form, Dirac-like, dispersion. So the ground state, we have, C of, C Majorana fermions. And as Yuji mentioned, with applying magnetic field, this Dirac cone can be gapped, and we have kind of topologically protected state, with chiral edge state, and that give rise to half integer quantum Summerfall effect. Fantastic. And some time ago, my Stuttgart colleague, George Jackley and Ginyat, Kalulin proposed, materialization of, this Kitaev model. And they kind of proposed if we have iridium 4 plus, uranium 3 plus, they have D5 configuration with spin 1/2 and the orbital moment -1. They form spin orbital entangle J1/2, spin 1/2 like moment. And in those compound, like alpha lithium iridate, sodium iridate, lithium chloride, they have honeycomb network of edge shared iridium 06 or ruthenium chloride hydra. And with this they showed we can kind of realize Kitaev model if only nearest neighbor interaction, super exchange interaction is kind of relevant. But in reality, as many of you know, all those candidate materials proposed say like 10 years ago showed long range magnetic ordering, either zigzag or spiral. So we have long range magnetic ordering instead of quantum spin liquid, at least in the zero field in this compound. And as Matsuda-san mentioned, we believe it is due to the presence of additional interaction other than Kitaev. And recently, towards Kitaev quantum spin liquid under such difficulty, 2 new arenas were developed. One, we kind of discovered, quantum spin liquid state in honeycomb, hydrogen lithium iridate. So we kind of replaced interlayer lithium plus with hydrogen. So we did a chemical modification. Okay, but honeycomb layer remains intact. But with this chemical modification, we found the ground state of this J1 honeycomb becomes quantum spin liquid. We didn't see any signature of magnetic ordering down to 50 millikelvin, and we got excited. And we kind of learned, this compound is extremely interesting quantum spin liquid. However, not, ideal playground to hunt, the Kitaev physics, unfortunately. For example, taking a look at specific heat at low temperature, we do see only T cubed, phonon contribution. And we don't see, large, magnetic, contribution coming from, Majorana expected for pure Kitaev model. And we did the isotope measurement. We replaced hydrogen with deuteron, and we discovered giant isotope effect on magnetic interaction. Okay, for example, like a Curie-Weiss constant gets doubled by deuteration, a huge isotope effect on magnetic interaction. However, quantum spin liquid state is quite robust against such isotope exchange, change of magnetic interaction. And such robustness is not expected for pure Kitaev model. It's quite sensitive to exchange parameters. So therefore, we concluded the ingredient other than Kitaev must be involved in understanding quantum spin liquid state of hydrogen honeycomb. So it's interesting to investigate, but the relevance to Kitaev is not clear. And in parallel with our discovery of hydrogen iridate, this honeycomb ruthenate under magnetic field emerged as quite promising candidate for Kitaev physics. And as I mentioned earlier, this compound shows zigzag magnetic ordering around 7.5 Kelvin. However, by applying magnetic field, this, zigzag magnetic order can, collapse. And, quantum spin liquid like, phase, shows up, above, 7.5 Tesla. That has been attracting considerable interest in the community. And in fact, colleagues, found that, many exotic, signature in this, field in this, quantum spin liquid, like, state, above 7.5 Tesla. For example, the group of Steve Nagler, Oak Ridge, they found that, continuum, spin excitation, above, 7.5 Tesla. And the, group of, Yoji, Matsuda, previous, speaker, as found that, signature of, a half quantized, thermal Fall effect, above, 7.5 Tesla. And in particular, this observation of, quantized, thermal Fall effect is quite important, and perhaps, need to be examined, reproduced. But besides, if we take a look at this, original data by Yuji Matsuda, carefully, as a function of magnetic field, we do see, well-developed, plateau-like, behavior. However, as a function of temperature, the measurement is kind of limited down to 3K. I think Pierre's, question, about that point. And actually, this part is this is kind of expansion of this part, and only down to 3K. It's not clear whether it indicates like this or there is plateau like state. So temperature plateau is not clear. Okay, so perhaps we need a measurement down to kind of lower temperature. And besides, quite, recently, a group of, phonons, he reported, their measurement on ruthenium chloride. And first of all, they kind of reported, there is large, thermal Hall effect, above, 7.5 Tesla, but, they show only below peak. And the magnitude of thermal Fall effect is like a half to 1/3 of half quantized value. Okay. On the other hand, they carefully investigated longitudinal thermal conductivity kappa XX, and they showed oscillatory behavior, and ascribed this oscillation to quantum oscillation of neutral particle. So I think the conclusion is something exotic must be happening there, but they couldn't confirm quantum Hall effect. So we are late comer to this ruthenium chloride business. But we thought we can do kind of something for that as a kind of late comer. First of all, we can examine half quantization independently from those two groups, and perhaps we can extend the temperature and magnetic field range, in particular temperature range down to low temperature below 1K. And maybe we can check structures in longitudinal copper, and we can ask kind of origin of oscillatory behavior, and so somehow we are lucky Yuji Matsuda kindly arrange we can access to so-called Bridgman single crystal. Made at TIT, and we measured the same Bridgman crystal as Kyoto group used, in kind of a Stuttgart. And as a reference, we have, another source of crystal made by CVT technique, okay, from, Bettina Lodge. And we kind of discovered that, this, CVT crystal behaves, slightly differently from Boltzmann, crystal, but the behavior is close to, the crystal Princeton group used. Okay, so this is kind of a picture of, our, crystal, Boltzmann crystal, the same as, Kyoto group, and this is kind of CVT crystal. So this is, a measurement of longitudinal thermal, conductivity, and this is, okay, this, will reproduce, report by other, group, including the Kyoto group. And we see anomaly at, Néel ordering, zigzag ordering 7.5, zero field. And, transition suppressed, and eventually gone. And after, zigzag order is, gone, thermal conductivity is enhanced, enhanced, reflecting, kind of a gap in magnetic excitation. And it's, magnetic field, dependence of longitudinal thermal conductivity. Okay, so now we are taking a look at the, horizontal scan. Okay, and at the low temperature below 1K, we see quite, complex, structure, and particularly we do see a very sharp, minimum at 6 Tesla and 7.5 Tesla, and this coincides well with two magnetic transitions, collapse of zigzag ordering, which you can see in the derivative of magnetization. Okay, so those two deep reflects phase transition, and of course here actually phonon thermal conductivity kind of dominant, and this deep represents kind of enhanced scattering of phonons by soft magnetic excitation at phase transition. But on top of this sharp deep at two magnetic transition, we do see kind of complicated structure even above 7.5 Tesla. Okay, and since we do see broad but well defined deep, we believe those deep represent high field hidden phase transition crossover. But of course I know Princeton group claimed quantum oscillation in kappa XX channel, and of course you want to ask me how about quantum oscillations. And at the moment we believe it is phase transition, not quantum oscillation. Okay, here actually I show kind of comparison of low temperature thermal conductivity as a function of magnetic field. Okay, our Boltzmann crystal. Okay, present result, and this is a reproduction of green is a reproduction of Princeton data in the Nature Physics, and the blue is our kind of a reference CVT crystal, and you can see okay those structure shows up at the same field. So the origin of those oscillative structure should be the same. Okay, regardless the source of single crystal. Okay, and then taking a look at detail, I cannot be positive for this quantum oscillation signal. First of all, we do see clear deep, two peaks, two oscillations apparently coincide with magnetic, phase transition at, HC1, HC2. And also, comparing with, CBT crystal, Bridgman crystal, I don't know the reason, but shows, higher thermal conductivity, but smaller, amplitude of, oscillative future. And of course, in general, with higher conductivity, you see bigger quantum oscillation, right? But it's kind of the other way around. So it's already kind of against the quantum oscillation in the picture. And then besides, if you take a look at temperature dependence of oscillatory structure, okay. So with decreasing temperature from 2.5 to 100 milli first this structure magnitude goes up, but then at low temperature it decreases. Or maybe this figure is kind of better to explain that. So this is magnitude of oscillative feature, and you can see at low temperature magnitude of oscillative feature kind of goes down, and this decrease was observed both Bridgman crystal and the CBT crystals commonly. Okay, and if it were quantum oscillation, you'd expect increase the oscillation down to t equals 0 limit, but in reality it goes down. So it's apparently against the quantum oscillation scenario. And finally, if you take a look at the position of those kind of dip, you can see dip position changes as a function of temperature. In fact, if we plot magnetic field dependence of dip and peak temperature, you can see kind of stronger temperature dependence of dip position, peak position. And recently, the August group, they kind of reported curvature of phase boundary associated with collapse of zigzag magnetic ordering. So this is kind of phase boundary between a zigzag magnetic ordering and paramagnetic phase. And they observed it's kind of the phase boundary tilts due to entropy effect. And those high field anomaly, we see quite similar temperature dependence kind of a tilting. Okay, so they behave like phase boundary. Okay, with kind of entropy influence. So from those we believe those high temperature anomalies around 9 Tesla, 11 Tesla arises from some sort of phase transition. Okay, and one of the kind of possible origin for phase transition is this topological phase transition Yuji Matsuda mentioned in previous talk. Now let me go to Summerfall effect. So we measured the Summerfall effect at first as a function of magnetic field. So we did this horizontal scan at the beginning down to 200 millikelvin, so below 1K. And this is summary of data. And first of all, you find the large signal of the order of half quantization. So this is half quantization value above 7 Tesla. Okay, and at kind of relatively low magnetic field below 11, 12 Tesla, with lowering temperature, the Summerfall effect kind of suppressed monotonically down to kind of a t equal 0 limit. Okay, and somehow it looked like no temperature plateau. And at the lowest temperature below 1K, we do see quite a complex, structure below 12 Tesla. And, at high field, above, 10 Tesla, okay, we do see, large, residual, thermal Fall effect. In contrast to, low field region below 10 Tesla. And somehow, something seems to be happening around the half, quantization, value. And of course, this field scan, unfortunately, our resolution is not, that, good. So therefore, we used that, a bit different approach. We did that, kind of what we call temperature scan. So we kind of scan the Summerfall effect, along constant magnetic field line vertically. Okay, this uses different experimental sequences, and we can get a bit better resolution of Summerfall effect in this kind of experiment. Okay, plotted by color. But let me emphasize that those two different experiment, horizontal field sweep and a vertical temperature sweep agrees quite well. Okay, and taking a look at this temperature dependence. Okay, so below 10 Tesla. Okay, right above magnetic critical point. Okay, you do see just monotonic decrease of thermal Hall effect, down to T equals 0 limit, and then no, half quantization plateau. But going above 10 Tesla, something start happening. Okay. Sorry, and first of all, you can see residual thermal conductivity, as I mentioned in the previous view graph. And besides, there seems to be something like kink, around the 6 Kelvin, half quantization value. Okay, so at high field, above 10 Tesla, something seems to be happening. And this, can be, kind of summarized, pictorially by, plotting, the value of, thermal Hall effect, by color. And in this, magnetic field temperature, map, this, white, region indicates, half, quantization value plus minus 15%. Unfortunately, we don't have that great resolution, but here we do see half quantized value within the 15%. Okay, and you see kind of a right now half quantization at low field, but at the high field, above 10 Tesla, we do see a kind of plane like half quantization value. Okay, and this plane of half quantization and kink at half quantization suggests those half quantization value has a physical significance. Okay, within a resolution of plus minus 50%. And of course, this Majorana edge state scenario plus phonon edge coupling can explain the presence quite naturally. But within our resolution, other scenario like magnon thermal Hall effect, pure phonons cannot be excluded, but they need to explain, reproduce the significance of half quantization value. And besides at low magnetic field, as I mentioned, you do see, quite, strong, suppression of, half quantization, value. Taking a look at this region, you do see a kind of a fine, structure. Like you see kind of a streaks, here. And in fact, there is, very deep, valley of, thermal, Fall effect, here. And that, field coincides with, what, we call the high field anomaly, HD1 and HD2, which, we ascribed to, some sort of weak, phase, transition, rather than quantum oscillation. So therefore, we suspect, okay, this, suppression of thermal Fall effect originates, from, some sort of, phase transition, high field, phase transition. And of course, some people might argue this, phonon, edge, state decoupling scenario. But we checked, phonon me free pass, here, and the phonon me free pass, hasn't, reached, dimensional sample yet, in this kind of a region. Okay, so this is kind of, what, we wanted to say for Kitaev, Honeycomb, system. And, so we wanted to say, this, half quantization value seems to have, significance. Okay, let me move on to, second topics, quickly, using remaining 10 minutes. So recently we extended in our kind of thermal transport system to this, Harvard, Smith site, Kagome. And essentially, Harvard Smith site, has, kind of pilocular lattice. And the pilocular lattice has, stack of, Kagome layer and a triangular layer and the Kagome layer, along, 1-1-1 direction. And in the Harvard Smith site, all, Kagome layer are occupied by S equal 1/2, kappa 2 plus. And the triangular site, ideally, fully occupied by non-magnetic zinc. Okay, that's, how, we can realize, spin 1/2, Kagome plane in Harvard, Smith site. But unfortunately, according to structural analysis, this, non-magnetic zinc site, certain amount of zinc is kind of replaced with, magnetic kappa. So there is, kind of a spin defect in this, non-magnetic, layer, and giving rise to disorder. That, has been kind of a source of headache, in the study of this, compound. But anyway, so in this compound, some time ago, people observed the absence of magnetic ordering, down to 50 millikelvin, despite scale of magnetic interaction is of the order of 100 to 200 Kelvin. And Yonsan Lee, using a neutron inelastic, scattering, identified, continuum of, excitations. And from those, people believe, quantum spin liquid, state kind of is realized in this, compound, and the spins are kind of fractionalized. And the interest of this compound is, experimentally, we might be able to, address the issue of, gapless or, gap G2 quantum spin liquid. So this, spin 1/2, Kagome, Heisenberg model has been studied quite extensively by, many fellow theory colleagues, and there are, tons of, papers you find in database. And unfortunately, this, debate hasn't been settled yet. And group A claims the ground state of spin of Kagome is kind of a U1 gapless with Dirac-like dispersion. And group B claims the ground state is a G2 quantum spin liquid with excitation gap, okay, small excitation gap. So therefore, there was kind of hope, using a quantum spin liquid state of Harvard Smithite, we might be able to address this, issue kind of experimentally. And in several years ago, a group of Takashi Imai kind of reported, beautiful, NMR kind of result. And they measured night shift, and they found that night shift decays exponentially. Okay, and this exponential decay means the spin excitation kind of a gap, and they suggested the energy gap, excitation gap over the order of 10K, okay, much smaller than J over the order of 100K. And by applying magnetic field, this decay changes from exponential to almost kind of a T-linear. So they suggested that with applying a magnetic field, this small gap collapse around 89 Tesla. So they suggested the gap to G2 quantum spin liquid. But 5 years after, the group of Filipino Mendels, they reported again the same night shift, but they observed, okay, even zero field, they observed T-linear decay of night shift. Okay, that means it's kind of gapless, and they suggested it's kind of U1 gapless quantum spin liquid with Dirac-like dispersion, which give rise to T-linear decay of night shift. And more recently, group of Takashi Imai kind of published kind of follow-up paper, and they said that disorder is kind of important, and there is a distribution of this case they measured the T1 instead of night shift. And they found that kind of a T1 showing exponential decay, and T1 showing kind of a power law decay, and they kind of suggested mixture of kind of gapped and gapless spin liquid due to disorder. So the situation is quite controversial. And this thermal conductivity has been measured by some groups kind of already, including a group of Yuji Matsuda, and they observed this T-0 limit. Okay, they don't see any finite T-linear term in contrast to this organic quantum spin liquid. Okay, so at least it includes well-developed Spinon Fermi surface. But of course, at the moment we discuss gapped or gapless, but with Dirac excitations. So therefore, the absence of finite kappa over T doesn't distinguish those two cases, unfortunately. So we wanted to proceed one step ahead, using kind of a thermal conductivity. And what we did was, it's quite simple, naive. So, the previous study measured the thermal conductivity, along the plane. But we kind of measured, thermal conductivity not only along, plane, Kagome plane direction, but also, perpendicular to, Kagome direction. That's, what we did. And we checked, kind of anisotropy of thermal conductivity. Okay, and here is, thermal conductivity along Kagome plane. and the thermal conductivity perpendicular to the Kagome plane. Okay, and actually, the thermal transport is dominated by phonon. Okay, the phonon is kind of three-dimensional, so we don't see, big difference, okay, in a zero field. Okay, it's almost isotropic. Okay, but applying, magnetic field, parallel to the plane direction. Okay, so you can see, magnetothermal conductivity. Okay, and as you see, out of plane component doesn't show any change, but the in plane component, you see negative, magnetothermal conductivity. Okay, so this magnetothermal conductivity is, quite, anisotropic. We do see that, only along the, Kagome plane. And we assign, this, anisotropic, magnetothermal conductivity to, scattering of phonons by, two-dimensional mobile, magnetic excitation with, momentum within the plane. So we captured two-dimensional, magnetic excitation, likely, Spinons. Okay, in this temperature, like 20, 40, 60 Kelvin. And of course, suppression of thermal conductivity means increase of two-dimensional magnetic excitation within applying magnetic field. Now, okay, so we take kind of a difference between 12 Tesla data and 12 Tesla data. So this is negative magnetothermal conductivity seen on the in-plane direction. Out of plane direction, it's kind of negligible small. Okay. Now, so using this, as the fingerprint of magnetic excitation. Now, what we want to do is, to see temperature dependence, because at which temperature we do see magnetic excitation, give us some hint, whether there is a gap or not. Okay, so if this magnetic component passes down to t equals 0 limit, that means gapless. That's what we wanted to see. But unfortunately, at low temperature, as you see, we see some positive component isotropically showing up both in plane and out of plane direction. Okay, so somehow those in plane magnetic conductivity consists of anisotropic to the negative contribution plus isotropic positive contribution. But since we can use this out of plane contribution as a kind of a reference to isotropic contribution, we can subtract this capacity as anisotropic component and estimate only anisotropic component like black. Okay, and at 12 Tesla, this magnetic excitation seems to be active, down to t equals 0 limit, suggesting gapless, magnetic excitation. But of course, in my group, suggested the 10K gap, and the gap, closer at 8 Tesla. So maybe this gapless behavior at 12 Tesla might not be surprising. So we have to see below 8 Tesla. And this is 6 Tesla. And again, we did the same, subtracted the isotropic component. And the anisotropic component seems to survive down to t equals 0 limit, still kind of gapless. But perhaps with these statistics, you might believe it. But fortunately, at low temperature, we have a bit better statistics. And this is low temperature only thermal conductivity under magnetic field, from 12 Tesla down to 0 Tesla. And you see, big, positive, magnetic thermal conductivity for out of plane direction, and the in plane direction. Okay, you see kind of a smaller positive. That means there is a kind of a superposition of negative, 2D component. And in fact, if we subtract, out of plane, reference from in-plane component, okay, so this is, negative magnetic thermal conductivity I mentioned at 12 Tesla. And with the decreasing field, this, negative, magnetic thermal conductivity persists, at least, down to 4 Tesla, well below, 8 Tesla, gap, collapse, field. So, and considering, kappa over T equals 0, and the persistence of this, low energy excitation, we believe, our kind of thermal transport, supports the presence of Dirac-like, gapless, excitation. Okay, perhaps, I have to stop now, but maybe let me, show, only one slide. Yeah, and let me mention about this low temperature isotropic component. Okay, and this low temperature isotropic. Okay, so this is the magnetic field dependence of magnetothermal conductivity at low temperature. Okay, so those come from this low temperature isotropic part, and you can see this in-plane component is superposition of a blue isotropic component plus negative part which represents two-dimensional magnetic excitation. But this isotropic part, if you take a look at the details, actually it's kind of positive at intermediate field, but at low field it changes kind of a negative. And this actually we can understand, as resonant, scattering of free spins, likely spin defect, between the plane. So it is, known, if phonon, thermal transport kind of dominated, and there is, free spin, there is, resonant, scattering of phonons by free spins. So this is kind of a thermally populated phonon density, and if Gman splitting, Gman energy is equal to the peak, resonant scattering maximized, and this gives rise to minimum in thermal conductivity. So this is due to resonant scattering. Of course, this phonon density peak shifts to high energy with increased temperature. Okay, and in fact, with increased temperature, you can see this, negative minima, goes up to, high magnetic field, consistent with this resonant, scattering scenario. So actually, from this, we are convinced that, this isotropic component we see at low temperature comes from spin defect in between Kagome layers. Okay, so here is kind of my conclusion, and thank you very much for your kind attention.
Thank you very much for this beautiful and instructive talk. The floor is open for questions. Rajiv, would you like to go? Oh, sorry.
Not me. I was just clapping. So Inti and Andre.
Yeah. Oh, yes. Okay. So yes, Andre, please go ahead.
Well, I think in fact Inti was first.
Oh, I'm sorry. Okay, Inti, please go ahead. Inti.
Yeah. So I just wanted so thanks here for the very nice talk. I just wanted to make a comment about this, let's say, dichotomy between oscillations versus phase transitions. Okay.
Yes.
So, I don't think one necessarily has to put this as two hypotheses that need to fight each other. Okay.
Mm-hmm.
Because the issue, okay, and this is something I was trying to mention in my talk, is that there is a crucial difference between spinons and usual electrons.
Mm-hmm.
And it's the following. So the spinon, in a sense, is some type of particle that carries a string. Okay, but this string, in a sense, is not important when you have the Fermi surface state. Okay, so the spinons deconfine, so to say, when you have the Fermi surface state. But once you apply a magnetic field, then you don't have the Fermi surface anymore, right? So you have some Landau levels for the spinons. So the question is, does the string become important once you remove the Fermi surface with these Landau levels, right? And so at least for the theory that I'm proposing, or not even within my theory, but it's reasonable that the string becomes important once you destroy the Fermi surface by Landau quantization, and the spinons could confine. The strings become, bind them tightly again. Okay. If the spinons confined in 2 dimensions, then you should have some kind of ordered state. So it is possible that what are some kind of parent state oscillations of the spinon Fermi surface state evolve smoothly into a sequence of confined states that describe ordinary phases with some type of order.
Okay, so you are saying quantum oscillation induces phase transition. Whenever Landau level pass, the chemical potential.
Exactly. Yeah. It's related to that, but it's not just that, right? So there is a question of confinement, right? So does the Landau quantized state of a spinons is still a spin liquid? So are spinons still there free particles, or do they cease to be free particles, and then you just get an ordinary phase with normal order, some spiral or something which actually has some low, expectation value of moments and so on. So it's not just quite the same as the electron. So the issue of a crossing of a chemical potential, but then there is, in the case of electrons, you don't have to worry about this nature of confinement, right?
But then can you describe collapse of zigzag ordering in terms of your picture reasonably?
Yeah, it's possible that, as I was trying to say, that the magnetic field, the emergent magnetic field, is some kind of type of correlation, like a spiral correlation, right? And then what is happening, when you have a Landau level, all you have is some kind of commensurability, an integer field Landau level, you have a precise commensurability between the number of flux quanta and the number of particles. So this commensurability could translate into something like the spiral locking into some particular commensuration with the lattice, right? So it could be just some transition in which the spiral is trying to change its pitch, but it's just locking with some structure of the lattice.
Okay, yeah, thank you.
It's still vague, but I'm just trying to maybe make a more general point that I don't think these are 2 things that need to be necessarily in contradiction. The fact that there are phase transitions and that there are oscillations.
Kitaev, what kind of phase transition did you have in mind?
Yeah. Okay. So I didn't have time to mention this, but so there is issue of 7.5K transition, 14K transition. So there are kind of 2 phases in this compound, and most of the sample we have additional phases kind of present, showing a transition at 14K, and this 14K transition collapse around the 9 Tesla that we know. So one of the possibility is unfortunately quite chemistry, but small admixture of 14K phase can cause another collapse of a magnetic ordering around 9 Tesla. Okay, but of course at the moment this deep around 11 Tesla, I don't see any, and the possible origin could be this topological phase transition Matsuda-san mentioned. Okay, so this deep coincide with magnetic field for topological phase transition Yuji Matsuda discussed.
So Andre, would you like to go?
Yeah, sure. Hida, I have so at some point in the talk, you showed the kappa XX over temperature measured by different groups, right? And you made, so
yeah,
I'm trying to clarify it for myself, and maybe this is evident. Sorry if you already said it. But so is the understanding that kappa XX, the longitudinal conductivity, is mainly transmitted by phonons, which are then somehow coupled to spins? And the reason I say this is because you show the data in 12 Tesla and 0 Tesla, and kappa XX is basically identical except at very, very, very low temperatures. So it looks like the bulk of it is transmitted presumably by phonons, something that doesn't care about spinons. But then at very low temperatures, you make a point that you could extract the power law, and if kappa over T is linear, then perhaps it's evidence of Dirac spin liquid. So maybe it's naive, but I seem to, somehow these two seem to collide in the way I see these two statements.
Are you talking about the Kagome?
Yes, correct.
Okay, sorry.
Right. For instance, yeah, the previous slide, even when you showed, if you wouldn't mind, well, yeah, let's say this, right? So if I look at this data, huge effect, right? But there is no difference between 12 Tesla and 0 Tesla. What am I to make out of this?
You mean, are you talking about this part?
Correct. Is this coming from spinons, or is that coming mainly from phonons?
We believe, majority kind of phonons.
Right, that's what I saw. So then the next question is, if you go one slide before, you show kind of the zoom in into there, for instance, at the very, very low temperatures, and try to make a statement that, well, I'm not sure what the conclusion was, but it seemed like if kappa over T goes like T linear, then perhaps it's evidence of Dirac excitations, right? So what is the statement? That at very low temperatures, the phonons freeze out, and that's why it makes sense to look at the spinon contribution? Is that the message?
Actually, no. Actually, so somehow, at low temperature, it decays like T to the 2.5, T to the 2, and we cannot distinguish, phonons or Dirac like magnetic excitations. That was kind of my motivation to do isotopy. So we need some kind of reference, to find your magnetic contribution. So this, we cannot distinguish magnetic contribution from phonon. So what we did that, applying magnetic field, pick out magnetic contribution, and use out of plane component as kind of a reference, subtract contribution from spin defect. That's what we did. And unfortunately, unfortunately, from this, it's hard to make a kind of distinction. Yeah.
I see. So based on what you just said, from your data, it's hard to say whether it's gapless U1 spin liquid or whether it's a gapped liquid, correct?
Yeah.
Gotcha.
Yeah, of course, that if it is kind of exponential, and contribution kind of large enough, like as Matsuda-san did, for this ruthenium chloride, we might be able to see a kind of exponential decay in kappa XX, but unfortunately we don't see that.
Yeah, thanks. Thank you.
Young?
Yes. So let me just follow up the Rajiv's question. Can you go back to the ruthenium trichloride?
Yes.
The oscillations, I just missed it because we have a zigzag phase, and then you are saying the first dip corresponds zigzag 2. And then the third one is also something to do with 14 Kelvin, which means another layer stacking different.
Yeah. Exactly. So, our sample, okay, majority is so-called 7.5K phase. That's clear. But
right.
we still see kind of trace of 14K phase, and as a function of field, 14K phase kind of suppressed, and then disappears, collapse around 9 Tesla, and that's it. So we suspect that, unfortunately, that might be, this, first one might be related to 14K phase.
Yeah, 14 case. So then the
Yeah,
where
but
you're
it's
19.
kind of too high to be explained by other phase. We checked the different field orientation, but you know, none of phase, you know, showed kind of collapsing at, you know, that, you know, high. Okay, so we don't have, you know, any kind of explanation for that. And one of the possibilities, you know, like you know, phase transition suggested by Yuji Matsuda, you know, topological phase transition. Yeah.
But the half quantization, where the kappa xy occurring half of those quantized values, is that the last one where you say that's possible?
Yeah, and these two anomalies, you know, somehow, you know, linked to, you know, kappa xy. So this is, you know, kappa xy,
Right.
and red means kind of a suppression close to zero.
Right. Yes.
Okay. And, so that means you have, you know, steep, deep, you know, those, you know, two places, and that is exactly, you know, what we call high field transition. Okay. Lower, I assigned the 14K phase, and this, you know, could be topological phase transition. Maybe actually I have better figure. Okay, I think you can see those kind of complex structure at low temperature. Do you see that?
Yeah.
Yeah,
Yes.
So those you know, contrasts, you know, come from this kind of complex structure, and those, you know, deep, okay, coincide with, you know, kappa XX deep.
So I mean, if this is the case, like because we have to think of a layer coupling, because what you're saying at a low field, zigzag 1, zigzag 2, now possibly even zigzag 3, these are different zigzag order along the different, you know, stacked layers.
Yep.
So that means that somehow the layer coupling is, you say that suppressed as the field is applied in the plane, and the system become more like a 2D like, and that's where we see the spin liquid.
Yeah.
Wait. I see.
Yeah, so yeah, I recognize this, you know, interlayer coupling plays kind of very kind of important role, you know, here. But unfortunately, you know, chemistry is kind of too complicated, and at the moment, I cannot, you know, give you kind of, you know, quite, you know, useful kind of information about that. You know, like comparing this CVT and you know, Bridgman crystal, you know, even at room temperature, stacking is quite different, you know, and the crystal structure is even kind of different. And, you know, we suspect that, you know, yeah, dots, you know, coupled with, you know, magnetic field and the two-dimensionalization you mentioned, you know, kind of, you know, playing a very important role, you know, here. But the chemistry kind of too complicated, and I don't know what's happening microscopically. But that's actually, since, you know, we are kind of materials group, perhaps, you know, we have to think about, you know, we have to investigate carefully from now on. Yeah. Right.
But I mean, this is because the interlayer coupling is extremely, extremely small. And so in principle, applying a field in a plane, you know, such an effect can be kind of, you know, understood, but why there has to be a difference between the A and B axis field then? I'm applying an in-plane field along the A versus the B, whether I have a C2M versus the P3112 or R3 bar, your A and B are still, you know, kind of differ, you know, same way. So I don't expect that the crystal structure will differentiate AB, but rather something more than that. Do you see the point? Like what makes the H along the A differ from the B? Like you're not going to get the zigzag 1, zigzag 2, zigzag 3 when you apply the field along the B axis.
Okay. So perhaps you know, I don't get you, but somehow, yeah, I know, you know, whatever the stacking is, you know, this orientation of hexagon is kind of maintained.
Yes, exactly.
Always this, you know, kind of a bond, you know, direction is perpendicular to bond is kind of A.
Yes.
And, you know, this corner direction is kind of B. That's, you know, common to all kind of stacking. Yeah.
Mhm.
So in that sense, global symmetry kind of maintained, but this symmetry was stacking kind of differs from material to material, and even within material, locally could be kind of different, and somehow taking a look at this discrepancy, from group, discrepancy from crystal to crystal. This tiny interlayer coupling kind of interlayer symmetry seems to play kind of some role here.
Mhm.
Yeah,
Okay.
but somehow chemistry can too complicated. Yeah.
Yeah, but I think it's fine, interesting. Okay, thank you.
So I wanted to ask a quick question. So in the context of the, the interpretation of quantum oscillations, I don't think anybody's really talked about the periodicity and of the oscillations. Is that, in principle, that should give you information about the volume of the Fermi surface, or is that not true for some thermal conductivity maybe?
Yeah, of course, Princeton group, plotted, oscillation as a function of 1 over h, like, classical quantum oscillation. And they see, different periodicity, at low field, below 7 Tesla and above, 7 Tesla. But they calculated the Fermi surface area, which gives like kind of relatively, small Fermi surface. Yeah. But yeah.
Okay.
Yeah, but this the calculated Fermi surface area is kind of different below 7 Tesla and above 7 Tesla.
Okay. Okay, so I don't see any more questions. I think we should thank the speaker again and close the session. So.